Hey, little sparklers. Continuing on, we're gonna now. I'll touch a few other videos about this, but really briefly, this is kind of how we talk in class about the difference between mass versus weight. So these are two things the public and general society doesn't see a difference in, but in science there is a big difference. So a few things just as kind of background. You guys all kind of know a little bit about gravity, and one of the examples I'll attach is the astronauts walking on the moon and just how different that looks and how much slower they come down. That is not because the astronauts are different. They're the exact same human they are on Earth. What's different up there is the force of gravity. So we need to make sure we understand the difference between something being weightless and then the myth of something being massless. And we'll kind of get into that. But the reason why that astronaut thing is different, the astronaut's mass is the same. If he weighs 70 kilograms on Earth, he is the same 70 kilogram human on the moon. However, because the size of the moon is different, the gravitational pull is different, so he doesn't accelerate to the ground as fast as on Earth. So let's dig into this a little bit. When we talk about weight, it's actually the force of an object due to the gravity pulling down it. One of the things that really I teach to help us understand this, how we measure something's weight in newtons, oftentimes is called a spring scale. Now I don't have one, but it's kind of like a fish. So if I'm holding up that spring scale with the fish, however much force the fish pulls downwards due to gravity is the amount of weight that will register on this spring scale. And that helps you understand it's not just how much stuff something has, it's how much force does it exert because of its mass. So it also kind of goes, I mean, this is just a normal bathroom scale, not a spring scale, but it goes with this same idea because when you step down on that, if I bend my knees really hard and go down, the number goes up because the force of me goes up because I'm pushing downwards. But when I just stand there, what that's measuring is the force I'm applying on that scale, and that force is all due to my gravity. So that's kind of what I really emphasize here. Both of these things, and really guys, weight is all about force that an object applies, and that is what's different on every planet. We measure this in newtons usually, although pounds is a different system, but our scientific system, we use newtons to measure weight. On the other hand, mass is the amount of matter an object has, and that never, ever, ever changes. So if we have a 30 kilogram bowling ball on Earth and we take it to the moon, it still is a 30 kilogram bowling ball. Its mass and the atoms it's made up of never changes. What changes is the force that it would apply downwards due to gravity. Okay, so this will hopefully help you kind of see this thing, but we have an object here. Let's just say it's a weight set, a bowling ball. Let's say it's a bowling ball. A 50 kilogram bowling ball has the same mass on Earth as it does on the moon. However, if we look, what's different is the weight, and the reason again goes back to the different gravitational pull. On Earth, that bowling ball would weigh 500 newtons, whereas on the moon, it's still the same bowling ball, it has the same mass. On the moon, the force of gravity is much different because the gravitational pull is different. Here's just another example to show you. The mass does not change, the weight is what changes, and that's due to the gravity. So this whole idea, and it doesn't go perfectly with this slide, but when astronauts are in the space station, you'll see them floating around. It's not because they're massless. We call that weightlessness, and that means there's no force of gravity. And when those objects are in free fall, that's a totally different thing in the space shuttle, but it's important you understand their mass is still the same. It's the weight that's different due to the difference in gravity. Just building on this a little bit, we can calculate somebody's weight on Earth very, very easily. And I put this all at once, but we know the net force according to Newton's second law is mass times acceleration. Now, if we're talking about an object in free fall, the only force acting on it is gravity. So that would basically show me that the force of gravity is mass times acceleration. And if we're on planet Earth, acceleration downwards is always 9.8 meters per second per second. We'll explore that as we go, but that's always the same for all objects. We'll cover that in just a sec. So what we instead sometimes call that on Earth is g, because it's due to gravity, the acceleration due to gravity. And on Earth, that's always 10. It's 9.8, but we round it to 10 for simplicity's sake. And again, that force of gravity we can call someone's weight. So if we take their mass times g, which is 10, that will give us the weight of an object. So There's that G on Earth we're talking about, and we don't use 9.8, we just use 10 because it's much easier with math then. This is very important you guys understand. I'll attach a feather versus an apple video, but everything on Earth experiences this same acceleration. The reason why we have a hard time understanding that is because of air resistance, and that video where they drop a bowling ball and a feather and they hit at the same time should help you understand that. Let's do one example here and then you guys are ready to rock and roll here. If we said what is the weight of a 75 kilogram man on Earth, a lot of people would put 75 kilograms, but we're going to draw a little free body diagram to help us. We're going to draw weight as a downwards arrow because it's the force of gravity. Force of gravity is the same as weight. We can calculate that by taking m times g. The guy's mass is 75 kilometers like the problem told us. Instead of 9.8, we use 10. So the weight, the force of gravity on that 75 kilogram man, or his weight, would be 750 newtons downward. Make sure we understand this idea of free fall, okay? So that's the end of that problem. That's how you'll do the practice ones. The idea of free fall is when gravity is the only thing acting on an object. So there's no air resistance, there's no side movement. If I throw a ball up and gravity is the only thing acting on it, we say that it's in free fall. And again, I'm going to attach this video, but it's important you guys understand everything on Earth falls at the same rate. It's the air resistance that really changes our mind there, and it's because of that force of gravity and how it's proportional to the object. So that covers that whole idea of free fall and an object's weight and gravity. Make sure we understand an object's mass does not change. Their force of gravity and their weight is what changes depending on what planet they're on. Because even if we go back to this example, if we went to Jupiter, this 50 kilogram person would actually weigh like 2,000 newtons because Jupiter's a huge planet and the gravitational pull is much, much, much higher, so they would weigh much, much more. Their mass would be the same though. Good luck on practice problems. Go get after it.